Okay, so um, welcome to the low-level programming in C, part 1. We will today first of all install the required development environment, and then we will start with the lecture from the get-go. So we are using Windows, but in principle you could use any other operating system as well, although Visual Studio will not work on Windows, so that will be somewhat more complicated for you to find out how to do things on the other on any other operating system. So here you can just go to or Google for the Visual Studio. I will put the link into the chat. Okay, visualstudio.com. As you see here, you can where is it? What we want the Visual Studio here. You can download the community edition free of charge. Wait, where is the download link? It's here. It's already downloaded. So I'll put this link into the chat. And the installer will take a second to execute. To press on continue. The installer is in German, but as soon as we have installed Visual Studio, it should be in English, so this won't be a problem. And I would recommend to anyone who is installing Visual Studio, of course, to install it in English. So here we can select Sprachpakete, and then we select English, because when you are getting some error messages or are searching in the internet how to do a certain thing, usually you will find results in English. And searching for German error messages usually will not give you much help. So it's, in my opinion, always best for programming related things to do everything in English. This just makes it much more efficient. So on the workloads page, as you see, you can do very many things, but what we need is here desktop development with C++. And the other components we don't need. Here on the side you get a list of other components which could be installed. For the most part, we already have all that is needed pre-selected if we select this. So then we can just click on install, and this will take a while. And like any good TV cook, I already have baked a Visual Studio before, and that we can just bring up front. We just need a second to boot. So there it's already installed, and after during the first start, which will be now for it, it will offer you to log in with a Microsoft account, or you can not log in. The thing about the community edition is, while it is free, it will after 30 days require you to sign in with some Microsoft account. So you can create a throwaway account if you like, which won't be used for anything else but to activate Visual Studio, and it's also free of charge. So they kind of try to force you to give them your data, but you are perfectly free to give them useless garbage data. And of course, for the sake of privacy protection, I would recommend to use as many disposable accounts as possible to make data collection about you as useless as possible. The installer would normally offer you to start Visual Studio instantly, but here, of course, for this installation, this wasn't done, so this is now the first start in this virtual machine. As soon as it opens, so here, as mentioned, we are just skipping the account for now. On the next page, you can select how the sub-windows of the main UI will be laid out, and also a color scheme. I prefer the light scheme, but which one you choose is up to you. And here I usually use the general layout, although you could also select one which is supposedly to be more optimized for C++. Which one you select really doesn't matter that much, since you can reposition all the windows later on, and it will remember your latest selection automatically. So before we get the main window, we get here this start page, which was introduced, I think, with Visual Studio 2019. And here we would see a list of open projects, which for now is empty since it's the first start. And then here we have a list of how we could start with a new project. Of course, we have options to check out an existing one, open an existing one, or create a new project. We also could select continue without code if you want to just get the main UI and bypass this window, but there is unfortunately no option to always bypass this window. So we create a new project, and for our applications, mostly we will be just using this simple console application. So it is it doesn't have any UI components. It is just a text input and text output to a text console On Windows, this works just fine. And any other sort of application which does graphical things is significantly more complicated. So since we are here diving into the deep and low details of C and C++, we don't need any graphical UI that would be in our way. We will do everything in the console. We can give it a name, so let's call it variables, since the first subject will be variables. And you can specify a location where you want the files of the project to be located. So by default it's under source in your user profile, but you could store them wherever you want. And there is also here another option which basically will create a subfolder with the same project name, and this for more advanced projects is useful to have. We will here leave this at default and press create, and it will create a Hello World project automatically for us. A Hello World project is basically a project which just prints or shows the text Hello World, and it is customary with programming languages to make as first project always a Hello World project for, well, some historic reasons. So we can first investigate the file structure which was created for us when we created the project. So we go to the place where the data was stored. Okay, here we have the variables folder, and inside of it we have this variables SLN, and again a variable subfolder with a few more files. Visual Studio is a very powerful and very advanced development environment, so it is optimized to work with multiple individual projects at the same time. I see there is a question in chat. So we will not be working with just single files. We will always be using Visual Studio and full Visual Studio projects. To answer the question in the chat, since it is more cumbersome to compile on in Visual Studio things from the console. You can do it. There is a build tool, but then if you would want to debug it, you would still need Visual Studio or WinDBG. So it's most convenient to just use the normal Visual Studio. So this to come back to this folder structure here, the solution file basically contains a list of projects. You can open it with a text editor. We don't have a text editor in this virtual machine. That is of course not great. I will then install a text editor which is much better than the Microsoft's one, Notepad 2. Okay. Oh wait, that was not the installer, it was just as if I was an installer for my setup file. Zack. Okay, now it's installed. Let's repeat that. You can press the Shift key to get the normal menu, or also you could disable the modern Windows 11 menu. But for now, we can do it like this. So, as you see, in this case, we have one entry here which points to the variables VCX project. So yeah, I should have not change the file association for Visual Studio for the solution file. When you open, by the way, a file a second time, it will complain that it cannot write to the default database, but you can just cancel out and close it again, so this is not a problem. Okay, so inside our variables project, as you see, we again have a couple of files. We have this VCX project, which is the main project file. One project basically describes, once you have created binaries from your source code, usually one binary. So it compiles to an exe file, to a library like a DLL, or a static library like a lib file. It can also compile to a driver, a control panel applet, or other things. And the idea is that if you have a complex project, or rather a complex solution of multiple projects, so you have something that contains an exe file and a library in the driver and something else, then you would have here in your solution, you would have multiple projects, and each of them would then compile to the necessary component, and these components can be interdependent. So when you click on solutions and then properties, you can specify project dependency. Of course, here we only have one, so there is nothing to specify, but this would define the build order. So if components need other components already be present, then you can use this. So this VCX project file, if we open it again with our Notepad 2, is as you see, an XML file, which contains project configurations and a list of files which make up this project. The filter file is basically, it shows here this representation as you see here. We have one source file, variables, but it's in like a virtual folder called source files. In C and C++, you usually have all your files in one directory, and then if you add them here, you can create a virtual directory structure to manage your files. If you want, and if you create a file here, let's create a header. Add new item header h. Then it is automatically added to this header files filter view, but it's still here is just created in the main folder where your project file lies. If you want to have on disk a folder structure, you need to create this folder structure manually, move the files where you want them, and then add them here. So if we, for example, remove header, we have the option between delete, which will delete it from disk, or remove, which just removes it from the view, but it, as you see here, is still present on disk. And then we can right click, add existing item, and then we have the header here again. So to illustrate this best, we can create here a folder, let's call it headers, move our header file inside, and then here we can re-edit. This is a bit confusing, since as you see, it is quite not how you would expect. You would usually expect that the folder structure on disk would be represented in the view here, and with a huge amount of modern programming languages, this usually also is the case, like C# and others. But for C and C++, which have a very old legacy to be compatible with, this is not the default behavior, so it behaves this way. And this filter file here contains this categorization, so it will have entries for every entry. The user file here contains a few settings which are basically specified by the user, and which do not need to be part of the project itself. Most of the project settings can be accessed by this properties menu. So all the things that you can set here will be reflected in the project file, although some of the settings will end up in this user file. And which settings end up where is up to Microsoft. They changed this also a few times in the past. So usually, if you want things to work the same way, you keep this user file also. Very old versions of Visual Studio, in fact, prefix the user file with the username, so that when multiple users on the same computer worked on the project, everyone could have their own presets. But apparently that wasn't a great idea, since they walked this back some versions ago already. Okay, so this much of the file structure. Here, as you see, there are really many things which can be configured. For us, only a few are important. But before we look into them, it's important to understand how usually compiling compiling is the process of turning source code into an executable file. So how this compiling works with C and C++ projects. Usually every file, so for example variables, CPP will be compiled into an object file. And if you have many files with source code, like variable CPP and then let's say function CPP and so on, then you'll get for each of them one separate object file. And then once this process is done, there is the last step of the compilation called linkage, which then takes all this half compiled, let's say, files, and then builds one binary out of it. Technically, the object files generated one can describe as they're as already being compiled, but the code is position independent and not linked with any other functions or things which need to be linked together. Linking basically means that things will get information integrated at which offsets in memory the other parts they depend on can be found. Okay, so let's quickly build the project. So we can here add many other menus like debugging and build menu, and the first button here will just build the project. Okay, it tells us where to put the file, to execute the executable file, but okay, let's copy the path. But an important thing to keep in mind here is that, as mentioned, it will have created quite a few more files. So it creates a folder, in this case named x86, which is the CPU architecture we are on, and it creates a subfolder for the current configuration. So here you can select between different architectures. Currently, by default, it always adds 64-bit, which is called x86, and so 32-bit, which is called x86, and 64-bit, which is called x64. You could also add, for example, ARM or other platforms if needed. And here you can have configurations. And in this case, we have the debug configuration. So it created those folders and put the files here. The PDB file is a so-called debug database. It contains information about how this executable is structured. So inside the executable, you don't have names of variables and also mostly no names of functions except for functions which are exported, which is only relevant in the context of DLLs mostly. So to know which offset in memory corresponds to which function or to which variable, you need such a debug database. And all the intermediate files have been created in another x64 and debug folder, but as a subfolder not of the solution itself, but as a subfolder of the individual project. And when we look inside, we see we have the object file for variables, and for any other C or CPP file, you would get one of these object files here. There is, of course, a way, if you don't want one of the files to be built, to exclude it from build. For example, if you added, let's say, you want to add some source code statically, and then you don't need all the components, and you could use this to disable it, but keeping it here sorted if you want. Okay, and as you see, it's quite large. So even this simple program with only effectively 5 lines of code gives us already a megabyte of intermediate files, which we don't need. So when you are submitting homework, then in principle you can either just pack the whole parent folder, although this .vs folder, which is hidden, you also don't want to pack, because this only contains configurations related to your local Visual Studio, so you don't want that to be uploaded, since it's also quite big and just wastes memory. Yeah, 56 megabytes, that's a huge lot. So ideally, what you can do is you go into the folder which contains your project file itself, and then you just select everything except the folder which have the intermediate files, and then you can just zip it. Where Windows even can zip files, and you have a super small file you can then upload to Moodle with your homework assignment. And if you see that the file is more than a few kilobytes, like megabytes or so, then you have added some files which don't belong there, and there is really no point in uploading those files. So it's recommended to always ensure that this works. And what also is good is that the project, of course, should be runnable, and when you submit homework, you should submit it in a way that it can be easily executed. So it should start and write what it's going to do, then do the thing and test whether the result is the thing that you expect it to be. And then, of course, ideally write like pass or fail on its own, so that one can quickly see whether the source code is behaving the way it should. Okay. As you may have noticed, we have here also this header file, which, as we see, has not created an object file. And the reason is that in C and C++, you have this different file functions. So a C or CPP file will contain your code, the things that will do actively things, so to say, while a header will only contain forward declarations, definitions, type specifications, and other things like that, which are needed but do not directly compile into executable code. With more advanced versions of C++, this whole thing gets a bit more convoluted and mangled together, so people sometimes write code inside the header, which then will end up compiled into the CPP files. But how this works, we will see in a second. For now, are there any questions so far? No questions? Okay. So then let's continue. Since the course is intended for people which already have some understanding in programming, as well as for people which are complete beginners for programming, it will contain a few things which might look very difficult, but it will also contain some things which might look very simple. So we will kind of start with the simple things and then quickly escalate to the very complicated things. So if you are on the beginner side and have any questions, then don't hesitate to ask at any point. Okay, so let's continue. So here in this automatically generated file, what we see is at the top we see a comment. A comment is basically any text which has no meaning for the compiler. It is just for the humans and in future AIs which are reading the code to help them understand what it is doing. You can write in your own words what the code is supposed to do, which meaning certain parameters and variables and functions and so on have. And whatever you write, it will not influence the resulting file which is being generated by the compiler. And in C you have two types of comments. You can have single line comments like this slash slash. So for example, slash slash test is a comment. You can also write comments after things. I'm a comment. Text. But what you also can do is, if you want, you can create so-called multi-line comments. And the multi-line comment starts with slash asterisk. And as we see here, Visual Studio actually tries to auto-complete it for us, and it already adds automatically this slash asterisk, asterisk slash to end the comment. And here, everything that's between those two symbols will be treated as a comment. So let's call this the interesting thing is that such a multi-line comment you can in principle create wherever you want, even within some expression. So what people sometimes do is that when they have some arguments and they don't want to use the arguments, but they want them to be there for reasons of compatibility, for example, that they then just comment them out inside the function definition and things like that. Okay, and since this whole Visual Studio behavior is a bit more annoying, as I said, it's auto-completing, for example, a lot of text, and I usually don't like this autocomplete behavior. I have a configuration file which I like to use, so we will import it in a second, and then Visual Studio will start behaving the way I like it. Whether it's the way you would want it as well, it's up to you. I can upload the file to Moodle if anyone is interested. But I think if you are starting, then you won't have any particular preferences with regard how you would want your Visual Studio to behave. And having things autocomplete things for you is kind of seems convenient. So tools, where was that? import export settings, import, next, browse. Oh, by the way, here you could also select any of the other standard layouts which you could have selected during the setup of Visual Studio. Desktop export 2024, next, import all, finish. It's saying that there are a few things which might be confidential, so maybe I will not put my file on the module. Now when we start it once more, so we should pin it to the taskbar since we will be using it very often. So as you see, now we have a proper title bar, no longer a menu in the title bar. And once it's done loading the program, you will notice that when I start a multi-line comment now, it does not finish it for me, so I need to finish it myself. And the way I write code is usually I jump around a lot. I don't like write it like people write a book starting at the beginning to end, but in a very dynamic way, and this autocomplete for my coding style is just unpleasant. So since we fixed this, let's continue. Okay, so so we have comments. So the next thing you see here is this include statement, and include basically means that you want to take another file in an abstract way and put it exactly here. So for example, if we would have something in our header file defined, then we could include it here. They call it header. For headers and headers. So we need to provide the right path, of course. And if we have different paths, you can select like root paths from which things will be included. In VC directories here, you can select include directories. By default, we have a few paths from the IDE, so the Visual Studio itself. IDE stands for Integrated Development Environment. And you can also here in C general additional include directories here specify other paths you want things to be included from. So for example, you could have s./headers, and then here we could if this works, include header directly. We would not need to provide its path. So this is quite convenient. And the way this kind of really works is that during a pre-processing step of the compilation process, so before actually the compiler starts compiling the code, when it sees such a directive, it will really take the text from the file and paste it exactly here, and then it will compile the whole thing. So of course, if you have multiple files, like let's create a second one, add, oops, not the fields, I wanted the file, add new item, let's call it source. Then just copy our header and include it again. And the copy didn't work. Then basically you would have two files and two object files which both contain the same informations from the header. And if you have only some definitions here, this is not a problem. But if you would have variables defined here directly and not just a declaration of a variable, then that would already be a problem. So we will try this in a second. But long story short, to not have such problems, you can use this pragma once directive, which will avoid some of these issues. And what you also could, of course, have is you could have recursive include. So you could have another header. Let's call it just call it source h, and this header could include header. Also, again, as I said, it will not have created the file where we actually want it. It created the file always on the root. So if we want it to be on the headers, we have to actually remove it here without deleting it, move it manually, and then re-edit. Okay, it doesn't like drag and drop. This way it always works. Oh wait, we already had header, sorry, I dropped the wrong file, that's why was complaining. Add existing item. Yeah, I dropped the wrong file. Also, another note is that if you are running Visual Studio with administrative privileges, drag and drop doesn't work. Then you always need to go through this add item. This is due to the security separation on Windows between Explorer, which is just a user process, and something that runs with admin privileges. And the reason to run Visual Studio with admin privileges is, of course, if you are writing and debugging an application which itself needs admin privileges, then you need to run the IDE, of course, also as an admin. So if we would here again include header, and then, for example, in our source file, in our variable, include header, and then include source, then it's kind of included twice. But this pragma once directive, it avoids this issue. It ensures that even if you have recursive includes or include manually the same header multiple times, only the first time it is encountered, it will actually be included, and any subsequent time this header is being encountered, it will not be included in the file itself. I see there are a few more questions in the chat. So if you have questions, you should really just speak up, because I'm looking only very seldom in the chat. So you don't need to do the same thing I'm doing here while I'm doing it here, because I probably will be doing it quite fast. So I would recommend that you just watch the recording, and then when you have all the time you need at your disposal, then try to create an own project and play with it a little bit. And there will be homework during this semester, which will be only based on what we see this semester. So there was a question with regard to the lecture that was the past semester, but the past semester lecture is actually the part 2, and this time this lecture is the part 1. So obviously part 1 is not dependent on part 2, but you can also make part 2 without doing part 1, since the two lectures are not that dependent on each other. So the part 1 is really like the low-level things, everything done in the console, etc., while part 2 is with the Qt framework, where we are actually creating graphical UIs and doing more advanced things. But in the grand scheme of things, it's still quite a low-level approach which we are taking during part 2. Okay, so we have this. So let's go to our variables. Let's see what we have next. Next we have a function definition. So a function in C is basically a subroutine which can return a value. Historically, there are some languages like Pascal which make a differentiation between a function and a subroutine, where it was that a function can return something that you can use it in a mathematical expression, while a subroutine does not. But effectively, this doesn't really make sense to make such a differentiation here. And in C you only have functions, but you can define a function as having no return value, just by specifying the void data type. But on functions we'll take a look in one of the upcoming lectures. So for now we will just take note that we have a main function, which is the entry point, the place where the execution of our code starts, and then things that we write in the main function will be executed, and when the main function ends, then the whole program will terminate. So and then of course here we have a not closer described line which just prints hello world to the console. And how this line works you will learn to understand in one of the later lectures, because it's actually quite complicated. If you want a simpler approach, you can include one of the standard libraries, stdioh. And another thing I forgot to say is that, as you see here, when I include files, I include some with this pointy brackets and some with just quotation marks. And in principle, this specifies where to look for the file. So if you use pointy brackets, it means it's some sort of framework file, so something that is part of your development environment, something that you can configure. Not here, there. in the include directories. So like here, for example, part of the Windows Software Development Kit or part of the Visual C++ itself. While the normal quotation marks means it's expected to be part of your project. But usually the behavior of the compiler is that it doesn't make a difference which one you use. Generally, so if you would specify a full path, it would have no meaning. If you just specify relative paths, it might sometimes work either way, and sometimes it might be a bit more picky. But it might have a small impact on the performance of the compilation because it's taken as a hint where to look for the file, and which include directories to process first. So it's good to do it the right way. But anyhow, we can call a function which then just takes a string and prints things to the console. And the other line functionally in a certain way does the same thing. It also calls a function, but it does it in a very convoluted way, which we will learn how to do a bit later. It uses a mechanism called operation overloading, which you can only do when you are already using C++, but for the very start we will do only C, and then once we are a few lectures in, then we will switch to C++ since C++ is much more complicated. Okay, so let's configure a few things which we will need. So generally just for normal purposes, let's say, the way such a project comes out pre-configured is already good enough. Here, by the way, before we change configurations, we can select the setup, the configuration and the platform for which we want to set this up. As you see, by default it creates two configuration, release and debug. And the idea is that the release configuration is intended to build a binary which you can ship to your customers or you can give to your friends in the lab to use every day. While the debug build is something that you use to develop and debug. The term debugging basically means searching for issues, searching for mistakes in the code and correcting them. Why it's called debugging, there are many historic sources. Some say that they actually found a moth dead in an old computer on one of the vacuum tubes, and that's how the term starts. But then others say that it was commented with the first real bug found in the computer, so I don't know why they call it this way, but that's by now its own terminology basically. And what differentiates such a release from such a debug build is that the release build will be optimized by the compiler a lot. So the code as you write it inside your functions, inside your program, might not look the same once it's compiled. The compiler might decide to remove variables. It might decide to remove entire functions, to so-called inline them, which means instead of having one function and calling it and then returning from it, it will just copy the whole code of a function and put it inside another function to avoid one unnecessary jump and so on. So it can be changed a lot, which makes attributing single lines of code to individual opcodes inside the program more complicated. And also when you are debugging things, you might want to have variables which are in the end not used, but which will contain values which we want to look at while debugging. And of course, having such dummy variables which serve no purpose in a release build would be wasteful, so they're all removed. And the other thing is that when you build for a debug target, then the libraries used by the compiler are libraries which have additional checks included. So if something goes wrong, then you have a good chance that this will be found instantly, and a so-called assertion will be triggered. An assertion is basically that the program flow gets interrupted and your debugger tells you something went wrong exactly there, and these assertions can also be linked with messages so that it even tells you what went wrong, why a certain parameter given for a function, for example, is in fact invalid. But those things, of course, in a release build would not only slow down everything, but they would, on such an assertion, effectively the application crashes. It's a intentional crash. It's called debug break, an int-free instruction. And you don't want this in your release builds, because you rather want your release build to silently ignore something if it can ignore it, then to crash outright. Although what you allow your release build to ignore and what not is of course always also a matter of security. So you don't want your application to just always ignore when everything goes wrong and then at some point allowing for some security exploitation and so on. But generally you would rather use assertions to ensure that, for example, people are using your library the correct way, providing correct parameters, and have additional, or to check, for example, if everything works as you expected and if you're not running into some unexpected situations, things which in a release build would, as mentioned, not only degrade performance but also would be usually not desirable. Okay, so this much these configurations, and of course you can create more configurations. You could have a separate configuration for beta testing which adds some checks but not all, etc. But here let's select all configurations and all platforms. This means that any change we do here now will be applied to all the different configurations. And we have here this SDL checks, which we can, I think, turn off, because what we want now during the first lectures will be really to study the code. So first of all, write some code, understand what it's doing, and then study it. What did the compiler made out of it? So for this purpose, what we want is the resulting code to be clean and readable. We don't want it to contain too many, for example, here the security checks. We also do not want. So we turn them off as well. What else? There was one more thing. SDL is off, security checks is off, just my code was the other one. Where is it? Yeah, this one. Support just my code debugging. This is a mechanism which kind of, when you're jumping around in your code, this is something that you will be doing later once you know how to use functions and things like that. But you can have obviously functions which you wrote yourself, and you can have functions which, like this printf, are provided by the C runtime or by a framework like Qt or like the MFC framework from Microsoft, etc. So some people kind of, if they only want to debug their own code, don't want to, when stepping through the code, to step into functions that are part of the framework. And this mechanism here allows you to automatically step over functions which you have not created yourself. But I think this is enough of disabling things. Let's quickly build the project just to see if it still builds, and then we will dive into it. So the project is called variables, so we will obviously start with variables. So a variable, as you might know from mathematics, is some abstract concept which can hold a value. In C and C++, these values are so in C these values are simple types or structures, and in C++ these values can also be complex types. What that means exactly we will learn a bit later, but for now let's take a look on what is a simple type. Well, the CPU as such can only operate on variable types which it knows, which it physically has been built to work with. And these are so-called machine types, and you can also refer to them as simple types. Obviously the most simple one is a character, so a byte, 8 bits long, my char, let's call it, and let's assign it the value 0. So in C, when you are defining a variable, you first specify the type which it must have. Then you specify the name that it will have. The name must start with a not with a number. It must be a letter or underscore. It can contain letters, numbers, and underscore. And when I say letters, I mean the American Standard Alphabet. You cannot use a umlaut or a sh or a j or any other more exotic letters. You are bound to just the printable ASCIIs, and you can use uppercase and lowercase, and upper and lowercase are treated as different ones. So if you define your variable in lowercase, if you want to refer to it, you have to refer to it in lowercase as well. If you would write the name using uppercase, then for the compiler it's a different variable. So in fact we could have mychar and mychar, and these are two completely different variables which have nothing in common, even though for a human being it's kind of the same thing because it's the same name. And this brings us, of course, to the next point, generally the way how you write names in C and C++. So for functions, it is the same restrictions. It cannot start with a number. It can start with an underscore, and it can contain lower and upper characters. And there are a few styles how you, because sometimes you might want to have a variable not just being one word, but you want, like here, my character, mychar, to be many words, and there are generally two styles how this is written. One is called a snake case, which is this one, and the other one is called camel case for whatever reason, where so basically here you separate words by using underscore as a stand-in for a space, which is good enough. In camel case you are saving on characters, but you are always starting with a capital letter if you start a new word inside of your variable name. But of course you are free to do whatever you want. You can mix it. It's not something the compiler would care about. In old school programming you were encouraged to use prefixes, like for example C my character, or if it would be a different type, then of course a different prefix, such that if someone sees a variable somewhere, then from the name itself the user can already find out which variable this is. But modern IDEs make this kind of completely unneeded, because usually if you move your mouse pointer over a variable, the IDE tells you directly that it's in this case a local variable and what type it has and which name it has. So you don't need to use this old school helpers. What is usually good is to prefix things which are a pointer with the letter P, but the other prefixes are more or less not necessary. And also the pointer prefix is just completely arbitrary, and what pointers are, by the way, we will learn in a few lectures, like many other things. So I said we are starting with simple things and building our understanding up. So for now we just have normal variables. Okay, and such a normal character, which is 1 byte, can have a value -1 to 8 up to 1 to 7. And it's quite peculiar that you have like by one more negative value than positive values, and this is due to how the binary representation of the values works. So we will take a look on this in a second. Important just thing to know is that this particular representation, even though kind of being a bit strange from this aspect, has a lot of advantages when implementing the actual mechanisms how then the operations work. Okay, so obviously one character is very little, so already 40 years ago, no more than 40 years ago, long time ago, people made computers which could work with larger data types. Of course, there were some proprietary systems from the mainframe time which had very odd byte counts, but within the x86 and pretty much any modern architecture, you always go in multiples of 8-bit bytes. So here the next one would be a short, which is it's called my short. Let's also give it the value 0, and it's obviously 2 bytes. Oops, 2 bytes. And this one can have a value from -32,768 until, let's align this a bit, 1 less. And the next one is called an integer, and int is like a char is always a char is always 1, a short is always 2, but an int, whether it's how big it is, actually might depend on the hardware platform for which you are compiling. So with Visual Studio, compiling for either a 32-bit Intel architecture or AMD 64, x64, an integer will always be 4 bytes, 4 characters large. But if you would be compiling, for example, for an Arduino using GCC, then the integer would actually be the same as a short. So this is important to note that that an int is just basically whatever the default int for a given platform is defined, and it's a peculiarity of x64 that even though it is a 64-bit architecture, its default int is still a 32-bit int. Okay, so let's call it my int. Let's again give it the value of 0. And if I write here before I write the other things down here, we can write other names that you could use for this short. So you can write, of course, just short, or you could write short int. That would also give you a short. Okay, and here, of course, now this is 4 bytes. I forgot the comment. Let's align things a bit more, and this is a 2 billion something something something. I'm too lazy to type it down. And like with the Visual Studio, I already pre-cooked a few things so that I don't need to type everything each time. And of course, this is then one less. Okay, then again, let's align those things. And there are a few aliases for integer, at least on the standard platform. It's called a long. And if you have an Arduino, and there, if you are using long, it will also be a 32-bit long. So like char, short, long, they are fixed and always will have the same byte length. You can also use long int. But the int itself might on different platforms be different. Since we are here doing things for modern CPUs on the desktop platform, even if you would be compiling things for ARM, like used in the modern Apple MacBooks and in the modern Copilot Plus PCs with the Snapdragon CPUs, or even compile things for a cell phone, an int for all those platforms will be a 32-bit thing. So it's easy to forget that it's not always true, especially since you are going to do things in science. You will be probably doing lots of things with Arduinos because they are cheap and convenient, and they are basically 8-bit CPUs, which as a standard length for an integer are only using 16-bit. So there it will be different. And if you would just, for example, send a data structure, what the structures we learn later from your existing desktop application to your Arduino, then the structure there would be completely invalid. It's simply because of such small differences. But okay, let's continue with the next data type that the CPU can natively handle. It would be a 64-bit integer, and the name for this is already not very nice. It's a underscore underscore int 64. My int 64 is 0, is 8 bytes, so the type there, and this is an even larger number. One less. Okay, I like the things to be nicely aligned, and strangely enough, sometimes just the way it wants to align things, it's not the way I want it. And you can use this alias here also long, which is strange, but they, when specifying the standard, decided to do it this way. So, well, and there are also like so these aliases here are like built into the language. If you include files like include headers like Windows H, which contains most of the necessary API definition to use the basic Windows functions, there the way it is that using compiler mechanism, they also have defined additional aliases which are soft defined. So this include directive here, there are other so-called preprocessor statements which you can use, like the define. Let's call it a word. And the way this works is you write hashtag define, then you write a name, and then you can write some code. And wherever you put word in your actual code, the preprocessor will go through your code and replace those things. So let's say a word on Windows is a short, a double word is a long, and a quad word is a int 64. So basically you could use here keyword instead of, oops, there is a space missing, and then it will of course then complain that this name is already used, so let's call it my int64b. And really the way this works is that this preprocessor definitions, that they're just taken, and then whatever stands here is then just plopped in this place, and when this is done, then the thing is compiled. So it is a very simple kind of process how those files are internally prepared before the actual compilation is started. And in some compilers you can set it up such that this preprocessed files can be outputted so that you can see what the preprocessor actually did. And you can also have more complex things. So for example, you can disable code blocks if you make a hashtag if 0 hash endif, then the whole code block from if until endif will effectively be just as if you would have cut it from the code. You can write invalid code there, whatever you want. The thing will compile because the compiler will ignore everything that's in between if 0. And if you want to enable it, it's if 1. And you could also write, for example, the name if def. So if a keyword is defined, then the code block is valid, and if keyword is not defined, then the code block gets disabled. So you can do such things which are quite useful, and they allow for quite a few nice tricks and to save on writing code. But we'll take a deeper look into those things later, because like what an if is already something for a later lecture. Since we are not doing control flow in the first lecture. In the first lecture, our program starts at the beginning and finishes at the end, and it does not change its control flow, its execution anywhere in the in-between. Okay, so we have here our basic integer types. And now we can take a look how this would look in the compiler, and also we will take a look how to debug things. So a very important mechanism when searching for issues in your code is to be able to break the execution of your program and to inspect what the program is doing. And of course, you could of course have your code run and then just press the pause button, but this would bring you to a random place in the code. You would need to be very good with your timing to break exactly at the right moment. So obviously that's useless, or at least it's mostly useless. It's basically only useful when you are debugging a loop which is executing endlessly. Then you just break somewhere into the loop and then just look why the loop is not terminating. And what a loop is, you will learn in one of the later lectures as well. So it's kind of difficult to talk about programming language when one tries to really build it up from the ground and assume no prior knowledge. But I think people can imagine something under a loop. It's basically just the same code executed many times until some condition tells the processor that it should not be repeated. Okay, but come back to here. So what we can do is we can set a so-called breakpoint. Here, usually you are doing it by just clicking on the left from your code, and then some indicator appears. In VisualStudio, it's a red dot. In other IDEs, this might be a blue arrow or whatever. And the way this works is that when the code is being executed, when the CPU arrives at the red dot, it will stop the execution, and the debugger will be notified that a breakpoint has been hit, and the debugger will then help us debug the current state of the application. So let's run the program. This is the first time we're actually running it with the debugger actually used. And here you see loading symbols. This is doing this because of my particular configuration which we have loaded. On your system it would not load those debug symbols, but instead just for system libraries, for the different DLLs that are part of Windows, it would just show you like the name of the DLL and then an address without telling you in which function of the DLL you are in. So the files which have been downloaded now are by Microsoft provided program debug databases for their Windows releases, and they do it for pretty much any Windows release that ever goes public. So yeah, so as you see, the thing broke. It put a yellow arrow on top of our red dot, indicating that it broke here. And here, when you go on debug and on Windows, you have a lot of debugger related windows, and for us the interesting one is the disassembly. And we have also a few more which I have already opened in the past, so I will just quickly close them and then reopen for you. So as you see here, the layout of the windows is part of the config, and if you load the config, then this layout is restored. So what did we wanted? Memory 1, and what we also wanted is registers. Okay, so and here, so the code we wrote is here, and when in the disassembly window, which it might also appear here in the middle, so it still appears where I had it last time. Usually it will just appear as a main view, but then you can drag it to the side, and then you will have a side panel so that you can watch both codes at the same time. And then in the view options, you could, for example, turn off the display of the source code. Although this is quite useful because then you see directly how a line was translated into machine code. But let's also add the bytes themselves. The addresses and symbol names sometimes so the addresses usually are not, they are just there, they are usually boring, they don't help or better or also not bad. The symbol names sometimes make things less readable, so we will turn this off for now. And as you see, there is automatically already some code created at the very beginning, just because the function started. And why this is, we will learn once I show you how actually functions work in more detail in C and C++. For now, we only care about the content, about what we have written here. So we have here a character. So basically what it does is it uses the move instruction to move a byte to an address. So here we have byte. PTR means that it will operate with a byte. It provides a pointer where, so a pointer is a memory address. It provides a memory address where to write, and as the memory address, it gives you this RBP, whatever that is, which we'll learn in a second, +4. And then, so the syntax is you have move, then you have where, then you have comma, and then you have what. And we always move 0, so we always assign 0, so it's always 0. Okay, and this RBP, what this is a so-called machine register. So when you go to debug Windows, you can open registers, which opens here, and you see here, well, first you can enable many registers. As you see, you have CPU, then you have CPU segment, floating point, MMX, etc., etc., etc. But the basic registers which are mostly relevant for us are these standard CPU registers. The whole rest we'll take a look at on some of them in a second, but most we will ignore. And such a register basically is a very, very small amount of memory, which is inside the CPU, very deep inside, and is connected to all the CPU's inner mechanisms, such that the CPU can actually do things. So when you think about it, for example, if you want to just make an assignment like with move, the CPU as such can only operate for the most part on these internal registers. In a complex instruction set language like x86, you can use such complex statements that you say take from a given register the address, add an offset to it, and then this gives you a memory location, and then write something to that memory location. So this works, although internally these operations are broken up inside the CPU into so-called micro operations, where in principle you have either operations which only work on registers, or you have operations which saves a value to a register or loads a value from a register into the large random access memory that you have. On rapid instruction set architectures like ARM, this is explicit. So you have a load and a store instruction, which you can use to store data to RAM or load data from RAM into registers. But all the other instructions you have, they will only operate on data which are stored actually in registers in the CPU. On a CISC system like this Intel architecture, which most desktops are, this is kind of hidden away. But for example, you will see that you don't have operations which would take two memory addresses. So at least one of them always needs to effectively be in a register. And the simple reason is, well, it has to be either the register or it can be a literal, i.e. a value which is written as part of the opcode itself. So the 0, of course, is not in the register. It is part of the data that are being fed with instructions. But there is no move like from one memory to another. You can move to a register and then move from register to memory. And other operations, for example, like if you do an addition or a multiplication, will behave in the same way. You kind of can specify as one operand a memory location, either directly or using pointer arithmetics. But you cannot do it like from memory to memory directly. It always needs to involve either a register or be just an assignment of static data that are fed through the instruction bus. And it works in a similar way for the other values here. So, for example, here to assign to short 0, the compiler decided that it would be more efficient to store in the register RAX, although it calls it EAX, which I will come to in a second why, at the value 0, and then use a move where it, okay, here it was a byte, now it says it's a word because it's 2 bytes, then it uses the same pointer arithmetics. It tells it will be that it's providing a pointer at the RBP plus 24, and then from this register the value should be written at this location. And it's important to specify the type so that the compiler, so that the CPU knows how many bytes to copy and to assign. And in x86, the nomenclature is like this: that you have, if you have a 32-bit register, the registers you have here, first of all, there are these ones do not exist. So for 32-bit, you have only those top registers, and they they are all prefixed with E instead of R. And if you want to use a 64-bit register, like okay, here we are doing it differently, but if you would want to use a 64-bit register, you would use here not EAX, but you would use just REX for 64. And if you want a 16-bit register, you completely drop the prefix and you just have AX. And for these registers, if you write code, you could write DR9 to specify that you are using a 64-bit R9 register, but only containing a double word. But you will not write assembly code by hand. So that's important for me, I think, to say that here, that you are not expected to write these things during the lecture. We are looking into these things so that you will learn a fundamental understanding how the CPUs works and how a programming language on the low level works. But the only thing that you will be writing during your homework assignments will be normal C and C++ code, like here on the left side of the screen. So this is just for your understanding. We will spend a lot of time in the debugger, I think, during the first lecture, so that you get a deep understanding of those things, but this will not be like tested whether you actually understood those things. So it's up to you to rewatch it on YouTube as many times as you think you need to get this understanding. And also, generally, it's like you don't need to know like what's the exact syntax for move, what's the exact register count, etc. It's just important to generally know that there are those things like registers, how function calls on a more abstract level work, and having seen this on the low level usually leaves enough residual information in most people's brains so that they will remember at least the core basics of how a computer works on the low level, which helps a lot when writing in a more high level programming language, because if you know what the CPU will do, at least roughly, it gives you much better control over what your code is actually doing. Okay, so this much to this assignment operations here, which are obviously quite trivial. We could take a look here on this debugger, so how this works. Obviously we have here some memory view, so we can specify addresses in memory which we want to view. We could, for example, use this RBP register. And what's the purpose of the RBP register and of the other registers exactly is, we'll take a look in detail when we are looking into functions. So for now, let's just say that the RBP points to the memory region which is available for this function to work with. And well, it's full of zeros because we will be assigning zeros, so it was pre-initialized with zeros. The register tab, obviously, as already mentioned, shows the states of the CPU internal registers. Then you have here a call stack, which basically contains a list which function, called which function, called which function, which we are right now. And once we learn about functions, then we will take a look on this tab here in more detail. Just as I said, here you see some Microsoft DLLs like NTDLL and kernel42DLL from which the execution of every thread and every process starts. And if you don't have a symbol loading enabled, then here it would only say NTDLL exclamation mark and a number, and here also a number. And it would only start showing names when it arrives at your own code. But for the purpose of this lecture, this is not so important here. Okay, and now to the behavior of the debugger. As you already noticed, it breaks the execution when there is a breakpoint, which is nice. But what else can you do? Well, you have here a couple of controls. So first of all, the stop sign, which just kills the process, ends everything. The restart is kind of useless because it just starts the application again as if you would press stop and then press run. I guess in some simple case where you have very basic applications, this is useful, but I never use it. Now the more interesting ones. First of all, you have here, it's a step into, which means that if you would have a function call, it would step inside the function and show you then what happens inside the function. Next one is step over, which unless you are on the call to a function, behaves the same thing. It just makes a single step. So we can test this here. If I make any of those two, we just advance to the next instruction, and it doesn't matter which one I pick, it always will do the same thing. Only if the instruction would be a call to a function, which we will learn again when we are learning about functions, then they would behave differently. And the last one, step out, is also function related. It means it will execute the current function until the current function ends, and then it will show you the code, whatever is then at the return. And since we actually have here a call stack, we can do that. You can step out, and as you see here, it brings us to actually existing source code, which is provided by Microsoft as part of the C runtime, and which invoked our main function internally. So, and then of course we could then continue with stepping until other things happen, but then we would just end up at the end of the program. So let's quit this and see what other types a CPU can work with. Obviously just these integer types for simple control applications, or for the purpose of what an Arduino, for example, can do. It's basically all that an Arduino can do. It probably doesn't, it certainly doesn't even is able of doing 64-bit. So Arduino will know char, it will know short, it might know int, but it's already not a given. But when you're actually writing code for an Arduino, you might probably usually be even able to use a 64-bit variable, because the code, so when you use this type, the compiler will know, okay, the Arduino doesn't know these types, but I can use many instructions to simulate the behavior, how it would work if it would have a 64-bit number. So it will be slow, and when you watch it in the debugger, it will be complicated. It won't be a single instruction thingy, but it will work, which is quite important, because in different use cases, for example, if you're writing to an SD card, you will need 64-bit numbers. Bigger numbers than 64-bit are not supported by compilers, at least not in a direct way. And if you want to use something that is bigger than 64-bit, then you will basically need to write your own implementation that will use the 64-bit or shorter instructions to emulate the behavior, how a number, which is for example 128, 256 or a kilobit large, how this would behave. And this is in fact done, and it's in fact very important because it is used by a lot of cryptographic libraries. So whether it's ACE, RSA, elliptic curves, etc., they are all computing with integers, but with very large integers. Especially RSA needs like a 4K bit integer to be reasonably secure. And with advancements in computing, especially with advancements in quantum computing, we will only see those numbers grow bigger. Or people might also decide to switch to other algorithms, but for now the simplest option is just have more bits than a quantum computer, and then it cannot crack you until it's big enough that it will. So, but anyhow, what other types do we have? So already very old CPUs implemented a floating point data type. And in fact, on the very first PCs, IBM PCs, you had like a CPU for integer, and you have a separate chip which you had to plug in to be able to use floating point mathematics. And of course, if you didn't have this chip but wanted to study the floating point mathematics, you could, but then it was emulated like the 64-bit numbers on the Arduino, which means it was atrociously slow. So it was a worthwhile investment, and yeah. And nowadays every CPU natively supports these types. It's float. Let's call it my float, and let's assign it a value 0.0f, and let's align it again, and it's 4 byte, and it can hold values from plus to minus 1.17549 plus minus again 38. So it's already pretty good for most things, especially if you are writing computer games or things like that. A float is the variable type of your choice. If you are doing AI learning, you actually want even less precision. Apparently even just as little as 4-bit floats are already good enough for some applications, which is crazy, but it works, so well, good. But if you want to do science, as upcoming scientists you probably want, you usually should use a double. It's called double because it has double the precision of a float, my double. And the interesting thing is that if you assign values, if you suffix them with an f, then it's a float. If you don't suffix them with anything, it's a double. And that it's a floating point number and not a integer, this compiler knows if you are using a dot. If you would be using just like, I don't know, 0, it will also work, but it's recommended to use it this way so that the thing always knows what you're working with. And it's for bytes, so it's 32-bit. So it's 64-bit. So in a way, even very old 16-bit computers already could handle, in some way, 64-bit numbers, but only as floating point with extra hardware. And this has an even larger value range, obviously. I mean 2.22507 e plus / minus 308, and this is usually enough precision for most things. So an important limitation is that there is not always like the ability to map a integer directly to a double, especially not to a float. So if you have an integer and then you make a double out of it and then you make an integer out of it, it might get some rounding error on the way. So this is something to keep in mind, and you really should use doubles if you want to do some mathematical scientific calculations. But if you are working with memory indices, if you are working with file offsets, etc., you should never use double, because due to the rounding errors you might get results which are useless for you. So for all those things you should always use integers. And again, let's run it. So we will see, of course, that here it will be using different instructions, but we also see that it is using different registers. So here we can enable the floating point registers and MMX registers maybe as well. So as you see, there are quite a lot of new CPU registers which have been added over the years. More and more and more and more, especially many with AVX 520, which is reasonably new. And all those registers, in principle, you could use them, but generally you would only use them when you write your own assembly code, which you probably don't want to do because it's really a lot of work. So those registers are usually used by libraries which have been written and optimized. So for example, if you do video encoding, audio encoding, or some matrix multiplication, some AI libraries, math libraries, they might use those registers. And while the first registers, the simple ones like the floating point ones, which we have here, are somewhat very similar to the registers we have here, just a piece of memory which holds a value on which you can perform an operation. Most of these modern registers, like here you see they're also like segmented here with these dashes in the way they are displayed. They are so-called vector registers. So the idea is that you can load a couple of numbers. I mean, for example, here in this SSE registers, you can load two 64-bit numbers, or you could also load for 32-bit numbers. Or with this AVX520, it's much more that you can load. And the way this then works is that when you make an operation on this register with, let's say, another register, for example, you could do you could add two vectors to each other in a simple way, like that you just add every value to the value of in the next element. Or if you can use functions, for example, if you want to set everything to 0 or so on. For matrix multiplications, you can use those operations, those registers, and it will be very efficient because it's doing like not just one operation, but it's doing 4, 8, 16 operations in parallel. So it obviously requires much more silicon space on the chip. It requires, of course, more energy, but it saves on time because those things are done in parallel. Writing normal code, as you usually do when you're writing and programming things, is not very easily parallelizable in this way. So if you want to do a Fourier transformation, then using such things is the right way to go. But if you just are programming like a sequence to move an actuator in your experiment, turn on a device, read a value from a device, then move some stage to a different position, such things, all of them will use either just normal integer math or maybe some floats if you want to calculate some positions very well in a more precise way. Let's say where you need the ability of a floating point number, where you want to calculate, I don't know, some radii, where you want to use pi and things like that. So all those vector registers, while there's many and plenty for us during this lecture, they will not be relevant. We will not be playing with them. We'll be only mostly focusing on just the normal integer registers, with a bit focus, especially during the first lectures, when we look on the floating point numbers, about how those work. But later it will mostly be just integer math, so that it's really like basics that you can also use on any Arduino without any emulation. That is good enough. Okay. So far everything clear? Are there questions? There's another question on the chat. Raspberry Pis. Raspberry Pis use ARM 64-bit architecture. Old Raspberry Pis use the ARM 32-bit. So in fact, if you have a Raspberry Pi 4, you can run Windows 11 ARM edition on it. Although only up to all releases up to 22.00. The newer ones, 28.000 releases of Windows 11 require ARM version 8.1, which would be a Raspberry Pi 5. So you can use it on a Raspberry Pi 5, but the Windows on Raspberry project kind of doesn't really support the Raspberry Pi 5, unfortunately. And while it works on the 5 with the smaller memory with 4 and 8 gigs, it doesn't work on the 16 gig version. And so obviously, since it's ARM 64-bit architecture, you can use values up to Win64 natively on it. ARM architecture also contains floating point numbers. I do not recall by heart if they have. I mean, you can definitely use float and double in your program, but if they have different registers for them, or if they use the same register, it's just truncated as it's done here for the integers, I don't know. And they have vector extensions in ARM v8, so all those vector operations, SSA stuff, you can do also on a Raspberry Pi. And if you have some math libraries, they will usually use those for computing wherever it is suitable. So for example, if you are using a package like MATLAB, it's a matrix computing platform with an own programming, well, own scripting language. It's not real programming, it's just a script, but it's very powerful and it's highly optimized. So when you use it the right way, then it will internally really use the most of what your CPU can do to provide you really good performance. In C, it is much more complicated. You will need to have either write a library that does it or find a library that does it the way you want it. Yeah. Any more questions? Okay. If there are no questions, then let's stop this program and continue with the binary representation. So as I said earlier, this is quite peculiar here that the negatives have like one more. And the reason is because basically 0 is one of the positive numbers in a way. Even though mathematically that's of course not anything you should say in front of a mathematician, I guess. Binary representation, so okay, positive values, space 0 1, that will be a lot of typing. Oops. Okay, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, yep. 16. Okay, so what we of course until now saw here is just how to provide a number as a decimal or here as a floating point. But when you're programming, you might also want to provide numbers in different notations. So you might want to provide it as a binary. So then you write 0 be 0, and then you write your wait, how many? 8 zeros, 1, 2, 3, 4, 5, 6, 7, 8. Okay, your 8 zeros. Or if you want to provide it as a hexadecimal, you write 0x 0, 0. And of course here it can be only 0 and 1. Here it can be 0 till f. And on a side note, in hexadecimal notation, like this one 0 corresponds to this 4 zeros. This can be 0 till f, and it's called a nibble. So like a bite, you can take a bite out of something, or if you are not very hungry, you can nibble on it, and a nibble is for bit. And sometimes it's actually useful to use individual nibbles, but there is no way to address them directly. You always have to operate with at least a whole byte. With regard to what the CPU is concerned, there are mechanisms in C and C++ which allow you to address individual bits of a variable, but this is something we will take a look at later. And the important thing to note there is, of course, that this mechanisms will generate more code because it will need to somehow pull out the one bit, do something with it, and then put it back in. So sometimes you might have like trade-offs between how much memory you want to use and how fast your code should be. On modern systems, speed is not really a limiting factor. On a small Arduino, it might be much more limiting. And by the way, the Raspberry Pi Pico is also a microcontroller, so it's like more like an Arduino than like a Raspberry Pi Zero or the big Raspberry Pi. Although there is, if I recall correctly, I think they have a 32-bit core, so they are much less limited and much more powerful with regard of computing than the Arduinos. Arduinos are like really the lowest of the low performance as you can get, but the upside is of course that they are extremely power efficient. Okay, so let's see the other numbers. We of course won't go through all of them, we'll just count through the first nibble. So obviously 1 will be 1. That is clear. So how does a 2 look? Well, a 2 is basically we're always just adding 1 from the side, and then you are just carrying over the one next. So this is obviously a 2. These ones here, as I said, they are A, B, C, D, E, F, 0 till F. And here we'll be basically then just adding always a 1. So 3 is 1, 1, 4 is 1, 0. Wait, yeah, 3 is 1, 1, and the other one is 1 0 1. So if you are counting binary on your fingers, you should avoid the number 4 because that's obscene. 5 is again, you just add 1. 6 is 4 plus 2. 7 is all ones. 8 is this. 9 is again, it starts here. Basically, we can just set this to ones because this will always be 1, and the bottom is basically just the same thing we already wrote down. Zack 1 1 1 0 1. This will always be set 0 1 1 0 1 1, and this is the first full nibble, 4 bits, and it's F. And of course, 16 will then be here. A 1 at the next. One set in the next nibble of our number, and then the same thing for negative values. Okay, so -1, zack, zack, 0, p, and -1 is pretty much the inverse of 0. It's all ones. 1 2 3 4 5 6 7 8, and this is also why we get one more negative value, because our -1 can use kind of the inverse of 0 plus then the system keeps counting. So here of course is 0xff, and the next one -2. -2 is basically the inverse of 1, so it has a 0 here. -2 will be ffe, and so on. So let's copy this. Let's copy a few of them. I think that might be enough, or maybe not. -2. I should have copied it with minuses. That would have been smart. 4 5 6 7 8 9 10 11 12 13 14 15 16 is the next one. Zack, and then we can copy. We can copy instead of copying this. Oops. Okay, so obviously then this will be 0 1. This will be 0 0. So it pretty much works the exact same way, just that it's kind of inverted, and there's one number x. This is always 0. This is then 0 0 0 1 0 0 0. Then we get here a 0, which will carry down all the way. 0 0 0 0 1 0 0 0 0 0 0 I'm off by 1, that's annoying. 15 should be 0 0. Wait, should it be? Oh no, I'm not off by 1. It's fine, because we have this one value more. This is fine. -16 is still contained within the nibble. So what were we? 0 0 0 0 1. Wait. 0. So we have here 1 0 0. So this will be 1 1. No, sorry, 0 0. Wait, the last one is 0 0. The one before that is 0 1. Should be 1 0. Unless I did something wrong, I think this is correct. And this one, of course, is kind of inverted. E D C B A 9 8 7 6 5 4 3 2 1 0. Yes, and if we would want to see something in the next nibble, it would be -17 0 p 1 1 1 0 1 1 1 1 0 x e f. Okay, good. And this brings us to the next thing about the integer numbers. Here we have defined them such that they can have positive and negative numbers, but often in programming all you need are positive numbers. So for example, if you have an offset somewhere on the hard disk, let's say a position of a file, there is the start of the hard disk, there are data, and then there is the end. There is nothing if you go the other way from the 0. So you can define all the types which we used to know and love as unsigned. For example, an unsigned int I int 0x1. You can assign it a value this time in hexadecimal notation, and you can do the same thing with shout, my ushout. Then of course this is let's say A, B, C, D. Of course it's shorter, it's just 2 bytes for nibbles. And then it changes, so for these positive values it changes nothing, just that all the ranges shift. Basically your end value is twice as much plus 1 because there are no negative values. And as you see here, the differentiation between positive and negative values, if they are signed, is that a negative value, the first bit is always set. While with negative values, with positive values, the first bit is always 0. But if you have an unsigned data type, then even the first bit can be 1, and it still will be considered a positive number, and used accordingly in different mathematical operations. So to summarize what I said here about these different representations, how you can assign numbers. Generally, when you have a fixed value in your program code, which is then assigned to a variable or used as an argument, it's called a literal. And what we also can do with variables, we can define them as constant. Int my decimal 1 2 3. So the const prefix tells the compiler that if you would try to change the value, that it will complain and not allow you to compile it. And while on a debug build, such a variable will usually have its place in memory, a release build might opt for optimizing it away and just inserting the value wherever it's needed. So yeah. Okay, next one. Const int my variable hexadecimal, that we also know. So 1 2 3 in hex is 0x7b. We should make a nice alignment. Then of course binary. My bin 0 b 0 0 1 2 3 4 0 1 2. And of course in C++ we always terminate every statement with a semicolon. And there is one more notation which might be a great source of great bugs, because there is such a notation like octal notation, which for the purposes of a CPU which operates in multiples of 8 bit is kind of useless. But for historic reasons there was compatibility for this added. And the way it is done is that you start like with decimal, but you prefix it with 0. 0 172 is the octal analogon to 1 2 3. And if you don't know that, you might think that you just will make this to make it look nicer, but this completely changes the meaning of your value. And the worst thing is, unless you're using like a number 9, which is not a valid number in the octal system, the thing will not even bug out. It will just say, okay, it's an octal number, and it won't be 1 2 3. So it's very important that you should never ever prefix your decimal numbers with a 0, because this will break things badly. Right, and what other literals do we have? Well, we have so obviously we have char, and a char basically is the same as a byte. Technically the difference is that a char is signed while a byte is unsigned. although nowadays with characters you are using also the upper half of the byte for different Latin 1 characters. So it's a code page called Latin 1, which is basically the English alphabet plus a few special characters, which for the most part of Europe were mostly like, okay, if we have those, we already can somewhat use a language. So we would find the and O and U and probably a sharp as S somewhere in this Latin 1 character set, as well as a few Slavic special letters. But if you go further away, you will not find those. So if you want to write in Chinese, Japanese, or Cyrillic, you will need other code pages, or rather for for Cyrillic a code page won't be enough. For Cyrillic we will need something called Unicode, and what that is and how it works we will learn later. Just one comment here about text in C and C++. The CPU natively cannot handle any sort of text. The CPU can only handle a sequence of bytes or a sequence of characters, if you will, and how this then is made to be a string which contains human readable text is very much up to the libraries that you are using. The language C and C++ contains a very simple type called a C string, but effectively this is a array of strings, an array of characters. So just multiple characters defined one after the other, and so on. And we'll take a look into arrays and strings and pointers in one of the later lectures, together with structs and so on, because this adds another aspect of that complicates things. But for now, it's just important to know that the CPU won't help us with strings. We need to do it ourselves, and C comes with a library and a simple standard representation, and how that works we'll learn later. But here, since we are looking on these literals, it's a good place to show you what other literals you can use if you are using characters. So first of all, you can use this single quotation marks, and in between them you can type a character. Since we use the number 1, 2, 3, let's use the character from 1 to 3, which is the opening curly bracket. You of course can assign it here to a character, sorry, to a char also as hex. Sorry, 0x7b. So even though this is a character, of course we need to change the name, otherwise it will complain. Let's say call it char1. You can also of course then use binary as well, but there's no point in duplicating what we already did here. So let's see on a few other ways how you can do the same thing. You can call it char2. So there might be characters you want to display which are not present on your keyboard, and if you want to have them in a string, you can write \x and then the hex value 7b, and then even though it's many characters, it will just basically be this one curly bracket, and with a curly bracket is fine. But if you need a character which is not on your keyboard, this would be the way to do it. There was another trick how you can do those things. I think if you hold down Alt and type on the numpad and then release it, then it makes, yeah, but I mean, you heard me, I typed 4 letters, I think you heard me, and then it made just one curly bracket. So in principle you can insert a character, but you might want a character which you cannot use. For example, you cannot use yet another single quotation mark. So in this case, what you actually can do is you can still use such an backslash, and if you write backslash quotation mark, then it will kind of escape it and not treat it as the end marker. And you can use \n and \r for new line and carriage return, but those are things which we learn when we take a look on strings. So here we are just about the literals, but since I already mentioned them, let's write them down. So we can have a n \n. That's a new line. No, that's a line feed. I mean, a line feed is a new line. Then you have R, which is carriage return. The nomenclature is very much made from mechanical printers. So a printer, well, even the somewhat modern inkjet printers have a printing head called the carriage, and it prints at some point. And if you wanted to return to the starting position, you send it a carriage return. And with old printers, which some of them were needle printers, so they were kind of flexible, they could make graphics, but you also had printers where you had like a wheel with individual letters and just one hammer that could just then hammer one letter from this wheel on the paper. So there it was really like almost like a mechanical typewriter, just that it was not that mechanical. And this is why the basic definitions for many of these control characters come really from the nomenclature of how printers would interpret them. So like new line really rolls the paper by a click or a few clicks further up. A carriage returns move the thing back, etc. And for example, in Windows, it's typical that if you press enter and when editing a text file, it will always create both characters, line feed and carriage return. While on Linux, they decided we are modern, we don't need a carriage return, we just need a line feed. So a file that comes from Linux will only contain a \n, while a Windows typical file will have \n. No, \r\n. First carriage return, then line feed. Right, and for example, you could have other, like for example, a tab, if you want a tabulator, \t, and a few others which we learn later when we learn about strings in C. Okay, and here, of course, the next interesting thing will be for us to have the const, which I already mentioned. So just that we have written down as comments, const int my const equals 1, 2, 3, and this is not editable. And I see we are already running out of time, so I think this is how far we can bring those things today before we start something. We're starting next thing, because it's, I think, not a great strategy to start something from scratch that we'll just need to break in the middle. So that much to this. I think what is good is if I tell you a bit more how the lecture will work. So mostly during the lecture I will show you new things. If you have questions, you can ask them. There will be no things that you have to do during the lecture in real life, in real time. You will get homework assignments. Now, since we are at the very, very beginning, you have just one unofficial homework assignment. Install Visual Studio and play with it a bit. This will not be tested on Moodle or anything. The newest code from each lecture I will always upload to Moodle after the lecture, together with a link to the recording on YouTube of the screen that you are seeing shared. The homework assignments will be a bunch. It always depends on the progress and how fast things progress, how many homework assignments they are during any given lecture. And at the end of the lecture, about a month before the semester ends, you will get a final project, which will be basically one large homework assignment. And the way this works is then the homeworks which are done during the course of the course give you about give you exactly 50% of the points, and the final assignment gives you another 50% of the points. And to get a positive grade, you need to have at least 50% of the points. So if you don't do any homework but do the final assignment perfectly, you can still get a 4, which for some might be satisfying. Of course, for most it shouldn't be. So you should do all your homework and the final project. And yeah, what else? There will be no additional homework like once the final project is assigned. Then you will really have like a month to do nothing else but the final project. If you have any questions, you can ask me always during the lecture. You can ask me always by email. It's better to ask than to not ask and then have something not work. Most homework assignments will be made such that you can write a test case for it. So this means that you can write a program and the program can tell you whether it did the right thing or not. So this is kind of helpful, because it's not based on you upload it and then you wait for for feedback. There will be no feedback on submitted homework. There will be just a final grade at the end of the lecture. If you are uncertain of what you have submitted, then you can ask me to provide you explicitly feedback, but normally the assumption is the homework should be self-testable. So if you submit it, you should be reasonably confident that it will work. The coding style and how pretty it is are not really graded. But of course, you should not try to write like the whole program in one line, because in C you could do that. It would just be a huge pain to analyze and debug. So try write it nicely, and also try to add comments. And especially if your program would not work in some way, the more comments there are, the more I can say, okay, this was okay, there is the problem. So it helps not only you to structure your thoughts and your program, it also helps me with then grading your submissions. With most of the homework assignments, there will be so-called optional points. So there will be some things that the homework has to do to get the full point count, and then there are things, if you want, you can do them, and this gives you extra points. So if you don't manage to do, for example, all the assignments because some of them were too difficult, maybe on the simpler assignments you opted to invest more time and do some of the optional points, then it can compensate for missing points in the main parts of other assignments, so that you can still have the full point count and a very good one at the end of the semester, even if you manage to scrub one of the more complicated assignments later at the end of the course. Of course, screwing up the final project is not recommended, then you would not get a good grade. So for this, take as much time as you need. The official submission, and another thing about the submission end. So whenever a homework is assigned, it is due 2 lectures down the road. So let's say if there is like a holiday and a lecture and another lecture, then it would be due in 3 weeks. If there is like Ostern, what's Ostern? Not Christmas. Easter holidays, I think it's like 2 not existing lectures. So whatever your homework you got on the last lecture before Easter, you have a month almost to finalize it. And the important thing is that there is always at least 1 lecture where you have the opportunity to, during the lecture, ask, okay, I was trying to make this homework, that didn't work. Can you maybe explain this part in more detail or something? So you can get more input and get some help, and then you still have 1 week to then submit it. That said, there are no point deductions from submitting it late. If you submit all your homeworks at the end of the semester, if we have not discussed the homeworks during the lectures, then this would be fine. Homeworks, as soon as the homework will be discussed during the lecture, that's the real submission end. But we will not discuss all the homeworks unless you want me to. So for some homeworks, you might have a virtual deadline at the end of the semester, but don't count on it, because on every next lecture, someone may say, oh, I had problems with this homework, or I did it this way, can we discuss it? And then you cannot longer submit it. So try to adhere to the official deadline. For the final project, if you need 1 week or 2 weeks more, then when the semester ends, then when the official deadline is, this is not a problem. I usually will start grading the final projects after 1 or 2 weeks. So if you need more than 2 weeks, then you should tell me that, because if I grade all the projects and I don't know that you will be late and you don't have submitted it yet, then I will say, okay, you have not submitted it, no points for the final project, and that would not be good, because then if you submit it then later, then this would not need to be changed in the system, and that complicates things. So if you have troubles with something, just communicate and it will work out fine. As said, as long as there is no pressing reason to deduct to not count something because of late submissions, it won't count for you in any negative way. Yeah. Anything else? I think that's it. Any questions? What will be the homework? Okay, there was one question in the chat. Well, there will be different homeworks. I think I cannot list like all of them here and now, but I can tell you, for example, what will be probably one of the first homeworks that you will get. So as you have seen here, we can of course assign numbers like in a simple way, and then what we of course can do is with variables we can do mathematical operations like addition, subtraction, division, etc., etc. But more important with regard to programming, what we also can do is we can do logical operations. So we can shift bits to the left, shift bits to the right, AND, OR, XOR, etc., invert bits, etc. And one of the assignments, for example, will be to only use byte operations to create numbers. So we are only allowed to assign one. Basically, you are only allowed to use numbers 1 and 0, and then you can have as many variables as you need, and then you can have to use binary operations to shift your 1s and 0s at the right positions to generate, for example, the number 1 to 3. So this will be one of the homework assignments. Another question here is, yes, I will put the link on to the recording on Moodle after the lecture. It should be there after about an hour. It always needs some time to transcode on YouTube before the link is ready. Okay, but to the homework. Another homework assignment which is usually provided quite early is to write, using such byte operations, a mechanism to convert from a integer number, from the binary representation of an integer number, to the binary representation of a floating point number. So the CPU actually has instructions to do this, but it is quite good for the understanding of how these floating point numbers are structured. Basically, the way they are structured is they have one bit as a sign, then they have a couple of bits as an exponent, and then another couple of bits as a mantissa. And you can always dissect any floating point number into these three values, which each of them is an integer. And the assignment basically will be just to have something where you enter a double and then you get the sign, exponent, and mantissa out, or something where you feed in sign and exponent and mantissa, and you get a valid floating point number as a result of this operation. There actually is a website I will link to where you can, which basically does the thing, but it does it in JavaScript, so it's useless for you, except for validating that your code gives you always the same values and results that this website gives you. So you can test your code against this, and then you know whether you did the assignment correctly or not. And I would always recommend to do a lot of testing, and when doing testing, it is very good to try to break things on purpose, i.e. enter invalid input and look or like input which is maybe not exactly invalid, but which is kind of close to invalid or very very edge cases. Always test all the edge cases and then look whether your code still behaves correctly. And of course, in more advanced things, if you have situations where you have any input, then you should always validate inputs, because like if you have a function, a program, something that takes some input, then usually there are constraints what constitutes valid input, and the expected behavior if you provide actually invalid input is the thing to say, hey, this is invalid, and fail gracefully, instead of trying to do something and then maneuvering itself into some unpredictable situation. Or rather, in computing, usually you don't really have unpredictable things, because everything is very very predictable, but what it is called is so-called undefined behavior. So basically, it's not predictable if you just read the documentation, and it might change from one version to another because it's just not part of the specification. So you should never rely on such undocumented behavior to remain constant. And of course, if you write your own functions and libraries, then you should try to make them validate input such that users cannot try to exploit such undefined behavior for their own purposes, because if you change something in the internals, that may break this, and then people might complain that, oh, but I always did it that way, it worked, and you say, well, yes, but the documentation said not do it this way, and now I changed something and now it's broken. You have to fix your code, and that may hit a lot of people depending on how many people are using your libraries. Especially nowadays with GitHub, where it's really easy to share your code to a large audience. You might find yourself in a situation of being a maintainer of some open source library that a few hundred or at least a few dozen people rely upon, and then of course you would want to make their experience as good as possible, and this would also include, of course, ensuring that when you keep developing the library, that they can just use it as a drop-in replacement for the previous version and not have something break because they did it not in the documented way, but it still worked. So it's always better to, in such situations, just return that this is not a valid input than to try to do something. Yeah, the lecture is another thing to say. The lecture is 3 Semesterwochenstunden, so technically it's 2 hours and 15 minutes, but it is planned for 2.5 hours. So usually, technically, we should have a 15-minute break somewhere in the middle or a few 5-minute breaks. Or if we don't, and I tend to not having breaks because I'm talking and talking and no one is saying anything, so I keep talking. So then we can finish 15 minutes early. Um, and there will be also times where I will just talk through the whole time without the breaks, and that will be 15 minutes extra. So uh, if I do that, then remind me of that. Then we will, in a few subsequent lectures, just finish half an hour early to compensate you for the time where you didn't have a break and I was just talking all the time. Yeah, and I think this is it. So we are this time 9 minutes early. But I assure you next time we will be over time. So we will get this 9 minutes back. Unless you have any questions, then I would stop the recording and stop the screen sharing and stop the chat and start uploading the things to Moodle and YouTube. So any questions? Okay, no one saying anything, nothing in the chat. Then I guess there are no more questions. So let's stop the recording.